Alright, so for the first half here of Unit 3, Homework 1, hopefully we'll get through maybe the first 6 or 7 questions or so. But anyway, question 1. An object is moving to the right and experiences a net force that is also directed to the right. So because the object is both moving to the right, so I know its velocity is going this way, and its net force is going to the right, which tells me that the acceleration, right, if the net force is going to the right, then the acceleration is also going off to the right. They do tell me that the magnitude of the force is decreasing with time, and then they ask me what the speed is doing. Well, the speed is still increasing, right? And the reason for that is, even though the acceleration is getting weaker and weaker, it's still always pointing to the right. And so since my velocity and the acceleration are both the same direction, I know that it's increasing in speed. So again, the major concept here, even though the acceleration is getting weaker, as long as the velocity and the acceleration are the same direction, we know that our speed is increasing. Question 2 looks like it's got a lot going on, so stalled car is being pushed up a hill at a constant velocity. The biggest thing though, right, the major concept that hopefully we remembered pretty quickly here, if something is moving at a constant velocity, then that tells me that no matter what, the net force, the total force, has to be 0, right? So my answer here truly is just 0, because if it's moving at a constant velocity, the net force, the total force, has to be 0. Now if they ask me for what the force of the people pushing up the hill was or something like that, this question would take on a slightly different spin, but our only option for this one that makes any sense is option A, the net force is 0. Question 3 is one of the ones that can be pretty tricky at first. So a 615 Newton student is standing in a scale, notices that the scale reads 645 newtons. From this information, the student can tell that the elevator must be moving. And the trick here is we know that because the student appears to be heavier than the student actually is. So again, we're standing in the elevator, right? The student notices that he or she appears to be heavier than he or she actually is. What that tells me is that the elevator is accelerating upward. However, I don't know anything about which way it's moving. The elevator could be accelerating upward and moving upward, so maybe it's going from the ground floor up and it's picking up speed, but it also could be moving downward while still accelerating upward, right? Maybe it's coming towards the bottom of its path and it's accelerating upward to slow down. The only thing I know for sure is the acceleration has to be upward. I actually don't know if it's moving up or down, right? So anytime we appear to be heavier than we actually are, it's because that acceleration is going upward. If we were appearing to be lighter than we actually are, the acceleration would be going downward, but again, I wouldn't actually know which way the elevator is moving unless they gave me some more information. So question 3, again, probably one of the trickier ones here. Watch out for it though, because we don't actually know if it's moving up or down. And then question 4, true or false question, and hopefully not a bad one. They do tell me once again that it is moving at a constant velocity. And because of that, I know that my net force obviously has to be 0. Since I'm not accelerating or decelerating, I'm moving at a constant. My net force then has to be 0. So then the tension in the chain must be equal to the weight of the car. Is that true or false? Well, if I'm dragging the car, it's a beautiful car here, I know, right? But if I'm dragging the car this way horizontally, then that force does not have to equal the weight of the car, right? Those two forces are perpendicular and therefore completely independent of each other. If it's moving at a constant velocity, the horizontal force needs to equal the frictional force, which would come from the coefficient of friction, so my mu of whatever static or kinetic friction, times my normal force, times my weight. But in this particular case, it does not equal the weight itself, right? It would be a coefficient times that weight. So don't let this one trick you. Don't overthink this one too much, right? If it's moving at a constant velocity on a horizontal surface, then my exerted force simply needs to balance out that of friction. So this is not a true statement. It is, in fact, false. Yet another question here that tries to trick you a little bit, right? So a 5 kilogram box, we've got two forces exerted on it, but it doesn't tell me anything about the direction. So if both of those forces were going off to the right, then potentially I would have a 15 Newton resultant going off to the right, in which case the acceleration would be, because the mass is 5 kilograms, the acceleration could be 3 meters per second squared. However, I could also have that these two forces are working completely against each other, right? So maybe I've got 5 newtons going off to the right and 10 newtons going off to the left. And again, there could be some resultant where the resultant here would be 5 newtons going off to the left, in which case the acceleration would be 1. Okay, so right there that tells me that both A and C are possible, and since this one does not tell me I have more than one correct answer, that tells me then that D has to be the right option. I don't have enough information to know for sure what the acceleration has to be. If you're curious, right on the 2.2, the 2.2 could just happen from maybe if I had those two forces that were pulling towards each other but not directly in line. So maybe I've got something more or less like this, where the 5 is pulling off at some angle and the 10 is pulling off horizontally. I could get 2.2 meters per second squared as well. Okay, so I just don't have enough information regarding the angle or the direction of these to know for sure which of those options could work. So again, option D, I just don't have enough information. So unlike most of the first 5 questions, the remaining questions we will have enough information to solve. Right? So the figure below shows the acceleration versus force graph for an object with 3 rubber bands, or 3 different objects, with rubber bands. They tell me then the mass of this second object, so represented by that second line in there. And then they ask me what are the masses of 1 and 3. Well, if I look here, right, they don't tell me the specific acceleration. They give me these kind of coefficients for A1. They just tell me it's multiplied by 5 or 4 or whatever. They do, however, give me the force, right, or the number of rubber bands here. Right, so really all I want to do to think about this is I'm going to think about my relationship in terms of force equals mass times acceleration. Right? I know the mass of object 2, and so I'm just going to kind of set that up with a proportion here to help me solve this. And obviously down here it doesn't actually say the force in terms of newtons, but for simplicity I'm actually just going to pretend that this is 1 newton, 2 newtons, 3 newtons, and so on and so forth. It actually doesn't matter if I were to scale this up by whatever number I may want to. But anyway, so I know I'm going to go ahead and start with object 2 because they gave me some information, right? They told me the mass of object 2. So I'm really just going to look then on this line and find a point or two that would work pretty well. So I'm just going to look, for instance, here at maybe this location, which looks like it's pretty close to the point 2, 2. Now it's not perfect, but it's pretty close to that point. So again, when the force is 2 newtons, I know the mass of object 2 was always 36 kilograms, that never changed. And I know my acceleration is in terms of this A1, so it's 2A1. Well, if I then just take this equation and solve it for my acceleration, for my A1, right, easy enough to do. I just kind of divide both sides by 2 to get rid of that. So then I have 1 equals 36 times A1, and so then A1 would equal 1 over 36. So what this tells me is that that constant there of A1 is actually just 1 over 36 in terms of the force of the rubber bands. And so then I can use that constant acceleration with my other two forces, my other two objects, I should say. So for instance, for object 1 here, once again, I'm just going to choose another point somewhere along that line. Now, obviously this point, there's no great point to choose from this linear equation, but maybe somewhere about here, if you want to say that's pretty close to 2.5, 2.6, somewhere in that ballpark would be fine. I'm just going to generalize that and say that's about 2.5. Again, it's not perfect, but it's going to be close enough to help me out. So then for that first one, when the force is 1, so again, I'm going right back to force equals mass times acceleration. When the force is 1, I'm looking for the mass, and I know the acceleration is about 2.5 a1. So it's about 2.5 times a1, which I've just defined as 1 over 36. So once again, it just becomes a matter of then solving for m. So m1, the first mass here, right, ends up being about 14.4, somewhere in that ballpark. Again, depending on exactly where you've rounded this off, your answers may vary a little bit, but it ends up being about 14.4 kilograms. And really all I'm doing is I'm setting up proportions for this, right? I'm taking advantage of the fact that I know that force always equals mass times acceleration, so I can solve for the acceleration in terms of my other measurements and then find it for each of those objects. So then doing the same thing for object 3, right? And just if I'm looking at this graph, start to think about it, right? But the mass of this third one should definitely be higher than 36 because the acceleration is not as steep, right? The acceleration goes up more gradually, and if I'm applying the same force but getting less acceleration, that tells me the mass has to be higher. But anyway, again, I'm just going to choose a point. So again, no right or wrong answer to this. I might even choose all the way over here. Again, I know that's not perfect, but it's pretty close to that point at 5 and then 2. So I'm going to say the force is 5, the mass is what I'm looking for, and the acceleration is about 2 times a1, so 2 times 1 over 36. And once again, I'm just going to solve for m2 here. Right, so 2 times 1 over 36 would actually be 1 over 18. 1 over 18, so multiply 18 by both sides, and I get about 90 kilograms then for that second mass. Again, the most important thing, these numbers may vary a little bit, but it should be clear that mass 1 should be lighter, should be less massive than mass 2, and mass 3 should be more massive than mass 1, or excuse me, mass 1 and mass 2. Okay, so anyway, hopefully this question wasn't too bad. Again, just interpreting from the graph, giving us a starting point, and then using that starting point to help us out moving forward. So then question 7 here hopefully isn't too bad. We're looking for the average braking force. So I'm looking for my force, and I know that force obviously again is mass times acceleration. And they give me a whole bunch of kinematics here to work with. So they give me the initial velocity of the car, they tell me the time that it takes, and then they tell me that it comes down and it eventually stops. So I know my final velocity of the car as well would be 0. Okay, so I've got those 3 pieces of information to work with. So this is truly just doing a step of kinematics and then plugging it into my force equals mass times acceleration. So if I do kinematics, I know my final velocity, I know my initial velocity, I'm looking for my acceleration, and I know my time. So plugging that in, I get 0 equals 27. Notice the units are what I want, they are meters per second, but make sure you're paying attention to that. And then 578 seconds. Right, so then solving for this, I obviously get a negative acceleration. So I get an acceleration that's negative 0.046 meters per second squared. So then if they ask me to find the average braking force, well, this is the only acceleration slowing it down. And so that acceleration is contributing to my average braking force. So then my force, which again is just mass times acceleration, would be 1100 kilograms times that acceleration, and I'm going to go ahead and drop the negative, because then in my answer I will just tell us that this is moving against the direction of the motion. Right, so again, just calculating this, 1100 times 0.046, I get about 51.4, and again that's in newtons, and I'm just going to say against the motion of the car, because I know that the car is slowing down, so it's working against the motion of the car. Right? Anytime the force and the acceleration are working opposite of the velocity, that's when it's going to slow down. So I avoided the negative by just throwing in that direction, that qualifier right there. But anyway, hopefully this question wasn't too bad. Again, pretty basic one, right? Just using kinematics and then our forces. Okay, so then the last question we'll get in this first part of the video here really is just a kinematics question, right? It's just going back to kinematics. The biggest thing that we need to work out here is, in order to find the acceleration, right, I actually need to find just the components of the acceleration going down the ramp. So I know gravity pulls straight down. Part of that gravity goes into the ramp and part of that gravity goes down the ramp, right? And so since this angle here is 15, just using a little geometry there, since that angle is 15, then I know it's the sine component of gravity that's going to go down the ramp. So my acceleration is 9.8, my acceleration due to gravity, times sine of 15. Which I end up getting to be about 2.54 meters per second squared. So I've got the acceleration down the ramp because there's no friction or any forces resisting this. I know that's how fast it's accelerating. They tell me that the sled starts from rest, so my initial velocity is 0. I do not know my final velocity, but I do know the time that it takes is 15.2. And so if they ask me how long is the slope, what is the delta x down the ramp, right? So if I'm looking for delta x down the ramp, I can just use my good old kinematics, right? My initial velocity times t plus 1/2 8t squared. So then delta x equals 0, my initial velocity being 0 simplifies it, 1/2 2.54, and then again times 15.2, but make sure we square that, and simply calculate that, solve that out, and we end up getting about 293.4. So hopefully this wasn't too bad, right? Once you get it set up, it really is just kinematics. The biggest step is making sure you're comfortable with the acceleration down the slope being just the sine component of the acceleration. But anyway, we'll pick up questions 9 through 12 in part 2.